Now that we've seen the statements of the comparison theorems, both the direct comparison test and the limit comparison test, we're just going to go ahead and jump into some examples. Okay. Now, for these examples, okay, I'm going to run through like the limit computations a little quicker than I normally would. Okay. Please review your calculus 1 if you need to. Okay. And most situations, when I can present a solution that uses either test, I'll do it. Sometimes one test is easier to see than the other. Usually that would be the limit comparison test. But I want us to get comfortable with using both the LCT and the DCT. So let's get into it. So our goal for this entire set of exercises is the following. We have a series. Is it convergent or divergent? We want to go ahead and use one of the comparison tests. Okay, so we're going to go ahead and get started here. We have this first one. We're summing 1 over n cubed plus 2. Okay, so you can do this in a couple of different ways. For me, I think I would probably start out by doing a limit comparison test. So let's do the limit comparison test here. Okay. Now, if I drop that plus 2, okay, let's think about something. If I drop the plus 2, we know that this sum here, the sum from n equals 1 to infinity of 1 over n cubed, we know that is convergent. Okay, we know that is convergent by the p-series test. Okay, recall the p-series test, all right? If I have a sum of form 1 over n to the p, and p is bigger than 1, then the sum converges. Here, p is 3. And 3 is certainly bigger than 1. So we'll use the limit comparison test, we'll use the LCT against 1 over n cubed. Okay, because our mystery series looks a little bit like 1 over n cubed, just an extra constant thrown in there. So we know that it should behave at least like 1 over n cubed, okay? We are only looking at the dominating terms, okay? So here we're going to set, okay, an to be the mystery series, 1 over n cubed plus 2, and bn is 1 over n cubed. Okay, and now we're just going to go ahead and compute the limit. Okay, we're going to go ahead and compute the limit that we need. So the limit here, as n goes to infinity, of an over bn, okay, so an is our mystery one, that's 1 over n cubed plus 2, and then when we divide by bn, we're going to multiply by the reciprocal, okay? So we're going to multiply by n cubed over 1. All right, so now we go ahead and combine everything. And notice here that I have a cube over a cube, okay? Now we can use our usual calculus 1 technique and divide by the highest power that it appears, so I'll just do that here. So the limit, as n goes to infinity of, if I divide top and bottom by n cubed, I'll get 1 over 1 plus 2 over n cubed, okay? The denominator there, 1 plus 2 over n cubed, that's going to go to 1 because that second term goes to 0, okay? So this limit is 1. 1 is a finite number. We know that our reference series, 1 over n cubed, that guy is convergent, okay? So the sum is convergent. So the sum converges. Okay. So that's how we use the limit comparison test. Now, can we also do this by a direct comparison? Well, it would take a little bit, but you can reason it, okay? So let's try to do this really quickly with a direct comparison test. Okay? And now we're going to use some of those basic inequalities from before, okay? So let's think about this, okay? I have n cubed plus 2, but Sean, it's 1 over n cubed plus 2. Yeah, I know, but we'll get to the 1 over part in a second, okay? Well, I have n cubed plus 2. I can make this smaller just by dropping the 2. Okay? So n cubed plus 2 is bigger than n cubed. We can all agree on that. Now, if I take reciprocals, okay, remember, when I take reciprocals, I reverse the order of the inequality. So 1 over n cubed plus 2 is smaller than 1 over n cubed. Now, I will convince yourself, or rather, suggest that you convince yourself of this by plugging in certain values of n, okay? Maybe n equals 1, equals 2, n equals 3, and you'll see, and you can actually show for each n, that the thing on the left is smaller than the thing on the right. Okay? But what do we know? Well, from the same thing on the left-hand side, okay, in black, But we know that this guy here, 1 over n cubed, that sum is convergent. And that's by the p-series test. So our mystery sum, okay, also converges by direct comparison. Okay, remember that for direct comparison, if the bigger thing converges, the smaller one has to converge. Okay, and we have established this ordering, okay, just by looking at these inequalities. All right, so that's an example. Okay, so that's an example using both the limit comparison test and the direct comparison test. Let's take a look at another one here. We have 1 over the square root of n minus 1. Now, this one you can probably think about, okay, for a bit, but let's look at it, okay? Remember, we want to try to look at the dominating terms, okay? So let's take a look at that denominator there, 1 over square root of n minus 1, okay? Well, the 1 doesn't really contribute much, okay? I still have the square root of n minus 1. Well, okay, but if you take, say, the square root of 1,000 and subtract 1, it doesn't really change the number that much. So we can think about this as just basically something like 1 over square root of n, and that gives you a hint as to what your reference series should be. So again, in black, if you want to use the limit comparison test, okay, we're going to compare against 1 over square root of n. Now, why over 1 over square root of n? Because that looks like our most basic thing if we ignore constants and lower order terms, okay, in both numerator and denominator, okay? And we know that this thing is not summable, okay? The corresponding sum, okay, 1 over square root of n is divergent. Okay, why? Because square root of n, that's n to the 1/2. 1/2 is smaller than 1, so by the p-series test, that thing is divergent. Okay, so now what we're going to do, we're going to call this an, this 1 over square root of n our bn. We're going to go ahead and call the 1 over square root of n minus 1 this an. It doesn't really matter which one you call them, but if you like, make bn your reference series, the thing that you're comparing against, and an the mystery series, okay? So we're going to go ahead and write our limits here. The limit as n goes to infinity of, well, we have an, so 1 over square root of n minus 1, times the reciprocal of bn, okay, just so that we're not worrying about complex fractions. Okay, once again, we multiply the fractions, square root of n over square root of n minus 1. Now you can divide out by the dominating term in both top and bottom. So if I do that, we'll get 1 over 1 minus 1 over square root of n. Okay, now think about it. 1 over square root of n, as n gets large, 1 over square root of n goes to 0. So that whole thing in the denominator goes to 1, and our whole fraction here goes to 1. So we got a finite number in the end. Okay, that was not 0. We know that 1 over square root of n is divergent, so the mystery series, okay, so the sum is divergent. The series is divergent. Okay. Again, that was just using the limit comparison test. Okay. Now let's see if we can do this with the direct comparison test. Well, you kind of got to be a little clever with this one if you want to use direct comparison. Okay. So direct comparison, okay, again, I may want to use the whole idea with 1 over square root of n, okay? But remember, for direct comparison, to show that something diverges, I need to bound this from below by something that does diverge, okay? And this may not be obvious, okay? But let's take a look at this, right? Square root of n minus 1, okay? I can make this bigger by just dropping off the minus 1, okay? Certainly, square root of n is bigger than the square root of n minus 1. Now again, we take reciprocals. I have square root of n minus 1, okay, in our denominator. That's going to be bigger than 1 over square root of n. Now remember, 1 over square root of n is our reference series, okay? But we know, okay, we know by the p-series test that this thing diverges. So the mystery sum diverges as well. And again, this is the sum from n equals 2 to infinity. Okay, so you see how we get the same result both ways? Okay, sometimes one test may be more natural to use than the other. Most of the time, you can easily do this with the limit comparison test. Direct comparison kind of gives it to you just straight up, okay? All right, so let's keep going. We got a lot of these to go through. Okay, so let's look at C here. N over n squared plus 1. Now, you can probably use a different test for this, maybe the integral test, okay? You have to verify the hypotheses, okay? But I'm just going to go ahead and do this one with limit comparison. I'll challenge you to see if you can find a solution that uses the direct comparison test. So again, we look at higher order terms, okay? And I'm going to go ahead and use this notation here. So we have n over n squared plus 1. This tilde I'm going to use is going to say asymptotic to or behaves like. Basically, if we drop off lower order terms, the thing will behave the same in limit. So the numerator, we still have n, but in the denominator, if I drop that plus 1, I get an n squared, okay? Now, n over n squared is, well, 1 over n. Okay, now think about our p-series test. Remember, that's our candidate p-series, okay, with p equals 1, that's the canonical harmonic series, right? And we know that the harmonic series diverges, okay? So we know that this sum diverges. Okay, don't let anyone tell you that that's minus a 12th, okay, because there's a bit of subtleties there. Okay, there's a number file video on that. All right, so we're going to go ahead and use our limit comparison test against 1 over n. Okay, so we're going to go ahead and call this guy our bn, and then the mystery is going to be an. Okay, we're going to follow that convention here. So we look at the limit here as n goes to infinity of an. Make sure you put things in the right place. Okay, times 1 over bn. Okay, an divided by bn, that's an times 1 over bn. So multiply by the reciprocal. N over 1. Okay, and once again, we multiply the fractions. So we get n squared over n squared plus 1. Okay, just like we do before, we divide out by the highest power, the highest order term. We'll get 1 over 1 plus 1 over n squared. Okay, but you can shortcut that and say that that is equal to 1. Okay, you can easily show that this is equal to 1. Again, please review your Calculus 1 knowledge on limits at infinity with rational functions. So we know that our reference series diverges. The limit was 1, so the mystery series must diverge as well. So this guy here, okay, n over n squared plus 1, this diverges as well. Okay, and we did that with a limit comparison test. Okay, so the challenge for you here is see if you can make an argument that uses the direct comparison test. Okay, now I should mention as we go along here that you don't have to always choose the same one here. There are multiple series that you can choose as your reference series, but you may usually want to choose the most basic one here, okay, even if you differ by a constant. Now, let's take a look at this one here, okay, log of n over n squared. And I'm only going to do limit comparison test for this one. And this is going to demonstrate that you may not get always useful information by the most natural choice of reference series, okay? So we're going to go ahead and do this with limit comparison test, but let's try to compare it against 1 over n. Okay, well, if I compare it against 1 over n, okay, we get the limit as n goes to infinity of log n over n squared times, okay, now we multiply by the reciprocal, n over 1. Well, I can drop a factor of n. So we have the limit here as n goes to infinity of log n over n. Okay, now if you're familiar with your limits, okay, you have infinity over infinity, so you can use L'Hopital's rule, okay? And so by L'Hopital's rule, okay, we'll get that this is the same as the limit of 1 over n at n goes to infinity, which is 0. But we know that the sum, 1 over n, diverges. That's the canonical harmonic series, right? So does this really give us any information? We have no information. we can't conclude anything. Okay, that's the problem here. Okay, let's go ahead and take a look at what the theorems were. Okay, if we scroll all the way back up here, if we want to use the limit comparison test, okay, if we want to show divergence, we have to make sure that the ratio is a finite non-zero number, or the limit has to be infinity. And it turns out, because I got a limit of 0, I got nothing. Okay, so we have to really keep that in mind here. So what do we do? Well, maybe let's try 1 over n squared. Maybe this thing converges. Okay, maybe it converges with 1 over n squared. Okay, so we do the same thing here. We have the limit as n goes to infinity of log n over n squared times n squared over 1. Well, the n squareds drop, we just get log n, but log n grows. It grows slowly, but it grows. It goes to infinity. Uh-oh. Well, that's a problem too, because the limit is now infinity, but we know that 1 over n squared, that is a series that converges, okay? P is equal to 2 here. So what do we do? Okay, I got no information out of this one. Well, it turns out, okay, we looked at 1 over n, it didn't really give us anything useful. 1 over n squared didn't really give us anything useful. Let's try something in the middle. Let's go ahead and split the difference. Let's instead try 1 over n to the 3 halves. Okay, let's go ahead and try that. Okay, so once again, the limit as n goes to infinity of log of n over n squared times n to the 3 halves over 1. Okay, when you do the work here, okay, you'll have log of n over the square root of n. Okay, and this is another case where we have to use L'Hopital, okay? Infinity over infinity, so we go ahead and take the limits, the derivatives appropriately here. So derivative of 1 over n, log n is 1 over n, and the derivative of square root n is 1 over 2 square root n. Okay, we clean this up. Okay, so we'll have 2 squared n over n. Okay, that'll simplify to 2 over the square root of n, and we can show when we know that this is equal to 0. Okay, so we know that we have a limit of 0. Okay, but I know that this thing is convergent. Okay, I know that this reference thing is convergent. Okay, the reference series is convergent. So, by the limit comparison test, our mystery series log of n over n squared, okay, summing from n equals 2 to infinity, or 1 rather, it doesn't really matter, that converges. Okay, this one is actually worked out in the textbook, okay. This is example, let's see, in my notes here, example 518 in section 5.4. Okay, this is worked out in the text there. They gave a pretty good explanation of this. All right, we're just going to keep powering on here. All right, 2 over 3 to the n plus 4. Okay, now we have some exponential stuff in there. Okay, now let's think highest order terms. Well, I know that exponentials dominate constants. Okay, exponentials dominate constants. So if I just drop off the plus 4 in the denominator, I have something that looks like 2 over 3 to the n. So by using limit comparison tests here, again, probably the most natural move here, let's compare against 2 over 3 to the n. Okay, well, what do we know about the sum? Well, if I write this, okay, 2 over 3 to the n, let's write it like that. Okay, understanding that, of course, I'm summing from 1 to infinity. Okay, 2 over 3 to the n I can write as 2 times 1/3 to the nth power. Now remember, this is a geometric series, okay? We have an exponential thing here. That's geometric. And the common ratio r has absolute value less than 1. So this thing converges. Okay, we actually have a formula for that, okay? So this thing converges. All right, so now we can go ahead and use the limit comparison test against this known convergent series, okay? So the limit here then goes to infinity of 2 over 3 to the n plus 4, okay, times, now we multiply that reciprocal, 2 over 3 to the n, the reciprocal is 3 to the n over 2. The 2's drop, okay, and now I have the limit as n goes to infinity of 3 to the n over 3 to the n plus 4. Okay, now we're going to do the same thing. We're going to divide out by the dominant term here. The dominant term here being the exponential, 3 to the n. Okay, so we'll have the limit as n goes to infinity of 3 to the n over 3 to the n divided by, now when we divide 3 to the n plus 4 by 3 to the n, we'll have 1 plus 4 over 3 to the n. Okay, now take a look at that denominator, right? 4 over 3 to the n, as n gets large, that thing, 4 over 3 to the n, will get small. That limit is 0. So the limit in the denominator is 1. I have a 1 left over in the numerator. I just have a 1. So we conclude that the sum converges. Okay, we conclude that the sum converges by using the limit comparison test. Okay, now you can also get this directly by using the direct comparison test. Let's show that really quickly here. Okay, let's show that by using the direct comparison test, okay? So, we know, again, we're going to use that same reasoning as before. 3 to the n plus 4, okay? If I remove that 4, I'm going to make this thing smaller. So 3 to the n plus 4 is certainly bigger than 3 to the n. Well, that makes sense, right? Okay, now I take reciprocals, okay? 1 over 3 to the n plus 4 is now going to be smaller than or equal to 1 over 3 to the n. Now I can multiply both sides of this thing by 2. Okay. We multiply both sides of this by 2. And because we're multiplying by a positive number, okay, we don't affect the direction of the inequality. But remember that the direction of the inequality gets reversed when I take reciprocals. Okay, now that thing on the right-hand side is convergent. That represents something that is from a convergent series. That is a convergent geometric series. Well, the same thing that we saw on the other side, right? So, by comparison, by direct comparison, I should say, so the sum converges. Because the bigger one converged, the smaller one has to converge as well. Again, you can use whichever test you want, okay? But here, I would probably suggest that using the limit comparison test is one way of doing these things. It's probably the most natural. Because the direct comparison test, you have to think about these inequalities. All right, let's keep going. Similar looking thing here, okay? 1 plus 5 to the n over 4 to the n. Okay, well, let's again think about these dominating terms, okay? In the numerator, the dominant term there is 5 to the n, okay? If I add 1 to a very, very big number, it doesn't really change the number that much, okay? So we can just think about this as 5 to the n over 4 to the n. And I want to try to compare this, okay? We're going to try to compare this against 5 to the n over 4 to the n. Okay, 5 to the n over 4 to the n is going to be my comparison here, okay? Well, think about this, okay? Again, we have these exponent rules, okay? I have a quotient of things that have the same exponent. That's going to be the quotient raised to the same exponents. That's how that works out. Quotient raised to the same exponent. Okay, but switch colors here. Okay, this is a divergent geometric series. Okay, because the common ratio here in absolute value is bigger than 1. Okay, so we're going to go ahead and use our limit comparison test here. Limit as n goes to infinity of 1 plus 5 to the n over 4 to the n, that's our mystery thing, times the reciprocal, okay, and I'm going to write it with the exponent on both the numerator and denominator, so we'll have 4 to the n over 5 to the n. Okay, the 4 to the n's drop. Now let's take a look here, okay. The limit as n goes to infinity of okay, 1 plus 5 to the n over 5 to the n, okay, and after doing the fraction operation here, we'll have the limit as n goes to infinity of 1 over 5 to the n plus 1, okay, but this goes to 1. Okay, so we get a constant that is non-zero, it's positive, okay, it's finite, but we know that our reference diverges. So the mystery series diverges as well. So the sum diverges. And we can even see this a little more clearly with the direct comparison test, actually. In fact, through the DCT, you can even get a more straightforward argument here. Okay, if you just look at the numerator, okay, 1 plus 5 to the n, well, if I drop the 1, I make the whole thing smaller. That's smaller than 5 to the n. Okay, now divide by 4 to the n, which is certainly going to be a positive number for positive n. So 1 plus 5 to the n over 4 to the n is greater than or equal to 5 to the n over 4 to the n. And once again, we get the same conclusion. I've bound this from below by something that's going to blow up, so the bigger one must blow up. So the sum diverges. Okay, this one is a very straightforward direct comparison argument here. All right, keep on going along. We got 4 more to go. Okay, now let's take a look at this one here. Cosine of n squared, okay, the square of cosine n, over n squared n, okay? I'll go ahead and help us out a little bit here. This n times square root of n, okay, if you use some exponent rules, you can write this whole thing as cosine square of n over n to the 3 halves, okay? Exponent rules, right? When we multiply with exponents, we add the powers. N is just n to the 1, and square root of n is n to the 1 half. 1 plus a half, 3 over 2. Now, this one, I couldn't really think of a good way of doing this with limit comparison, but direct comparison is probably the powerful thing to do here. Okay? Direct comparison is very powerful here. Okay? And why is it really powerful? Well, we know the following. Okay, here's something that we know. Okay? We know that cosine square of n, okay, the cosine function is bounded above by 1. Okay, it can get no bigger than 1. Okay? So, we have that inequality. That is true. Now let's divide both sides of this inequality by n to the 3 halves, which is certainly going to be a positive number. Okay? Whenever I take even-powered roots, I always have to get a positive number. Okay, so we have that cosine square of n over n to the 3 over 2 is less than or equal to 1 over n to the 3 halves. Okay, but now we got to take a look here. This is a p series where p is equal to 3 over 2, so this is convergent. Okay, that represents a summable series, okay? And so, by conclusion, okay, by comparison here, because the bigger one is convergent, the smaller one must also be convergent. So, the sum converges. The sum converges by direct comparison. Okay? If you can figure out an argument using the limit comparison test here, more power to you. I found that the direct comparison test was the most straightforward here. All right, let's take a look at this next one here. This one looks a little funky. Not that one. Come on, stop scrolling. There we go. We have 1 plus 2 to the n over 1 plus 3 to the n. Okay, now this is where this idea of thinking about dominating terms, okay, comes in. In the numerator, the 2 to the n dominates, and in the denominator, the 3 to the n dominates, okay? So I can probably think about this if I wanted to, say, use the limits comparison test, which is, again, the most natural way of doing this, in my opinion. If I wanted to use the limits comparison test, okay, I'm going to try to compare this against 2 to the n over 3 to the n, which I can write as 2/3 to the n. Now, why this choice? Okay, well, I know that 2/3 to the n, that is a that represents a geometric series, okay, where the common ratio and absolute value is less than 1, so it's convergent, Okay. And once again, we're just going to go ahead and do the same game here. Okay, so we're going to look at this limit here. As n goes to infinity of 1 plus 2 to the n over 1 plus 3 to the n times, now we multiply by the reciprocal, 3 to the n over 2 to the n. Now, you can do some shuffling around with the commutativity of multiplication here and everything. Okay, so we can have this, write this as the limit as n goes to infinity of 1 plus 2 to the n over 2 to the n times 3 to the n over 1 plus 3 to the n. Okay, now it's a bit of an exercise, okay, but again, thinking about for both of those grouped factors, if you want to call them that, thinking about this, if you want to divide through by the highest dominating thing in each thing, so in the first group, we're going to divide through by 2 to the n, so we'll have 1 over 2 to the n plus 1 on top, divided by 1, and then the second we'll divide out 3 to the n. All this to say that the limit is 1. Okay? Again, I'll leave that as an exercise. But we have here that the sum is convergent by limit comparison. Okay, so that's doing it by limit comparison. I won't show the solution for direct comparison. You can actually really easily get away with this for direct comparison if you're pretty clever with some of the inequalities here. You can actually use the same reference series, and I'll leave that as an exercise, as a nice little challenge for you.
You may notice a little bit of a costume change and a bit of a cut. That's because when I originally recorded this, there was a mistake, and a student emailed me about it a week later. So sorry. We're going to go ahead and correct this. Let's take a look at this series once again. All right, we're summing something that looks like square root of n plus 1 minus square root of n over n. Now, you're going to have to actually prime this a little bit before you can actually make a conclusion about the convergence or divergence of the series, okay? And this is going to go back to something in Calculus 1, okay? Or really, it's just really an algebra trick. And the idea here is to multiply by the conjugate here, okay? So we're actually going to use the fact here, okay? And we're going to use this fact here of the difference of squares. That in the following, we have a minus b times a plus b. That multiplies out to a squared minus b squared. Now, you might say, Sean, I don't see squares in here. And it's like, well, of course not, because you see square roots. But you can use this for any kind of a's and b's, okay? Be them logs, exponentials, or even square roots. And so what I'm going to do here is we're going to prime this, okay? So we're going to rewrite our summands here, square root of n plus 1 over minus square root of n over n. I'm going to go ahead and multiply and divide by the conjugate, okay? So we're going to go ahead and multiply and divide by square root of n plus 1 plus square root of n. Okay, so we're going to go ahead and do this top and bottom. Okay, and this guy is the conjugate, okay? Here, we're going to go ahead and treat square root of n plus 1 as our a. There you go. And then we're going to treat square root of n as our b. Okay? That's exactly what we're doing there. And now when we multiply this out, okay, this is just a little simple algebra exercise. When we multiply this out, we'll have n plus 1 minus n in the top, and the bottom will have an n times square root of n plus 1 plus square root of n. Now we go ahead and do some tidying up here on the top there. N plus 1 minus n, combine like terms. N minus n is 0, so we have a 1 over n times this square root stuff. So square root of n plus 1 plus square root of n. Now, this is where we're going to go ahead and do some thinking here about what kind of comparison to use. Okay, there's a couple of things that you can try here. And let's try to think about this in the most direct way, okay? Not by the direct comparison test, that wasn't a joke, but we're actually going to try to use the limit comparison test. So let's try to use the limit comparison test, but this time we're going to compare, if I can first spell compare correctly, we're going to go ahead and compare against, surprise, 1 over n to the 3 over 2. Now you might be thinking, well, how did you get that, okay? Well, let's make an observation here, okay? If I look at the highest order terms here, basically note that square root of n and square root of n plus 1, they basically behave the same, okay, up to a constant, all right? But let's make an observation here. If I look at the highest order terms here, we have n times the square root of n, okay? Well, if I think about my exponent rule, it's n times n to the 1/2, and then I add because I'm multiplying with exponents, well, n times square root of n, that just ends up being n to the 3 over 2. And that's where I got that denominator there. And so what we're going to do is we're going to use limit comparison against this thing. Now, of course, we know, okay, we know that this reference series, okay, the sum from n equals 1 to infinity of 1 over n to the 3 halves, we know that this thing is convergent by the p-test. And why? It's because the p is strictly bigger than 1. So we're going to go ahead and set up the limit here. So to that end, we'll do the following. Okay, that's the solution to the next one. You shouldn't have seen that already, but that's fine. Okay. So we're going to go ahead and compute the limit of the quotient here. So the limit as n approaches infinity of the mystery series, so square root of n. In fact, I'm going to go ahead and write it using the simplified form here. So we'll have 1 over n times square root of n plus 1 plus square root of n, and then times the reciprocal of the reference, okay, n to the 3 halves over 1. Okay, and now I'm going to go ahead and do a bit of trickery here. All right, so to say, it's just really an algebraic step. Okay, so on top, I'll still have this n to the 3 over 2. I'll go ahead and multiply through. Okay, so we'll have n times the square root of n plus 1, then plus n to the 3 over 2. And then as I've said, right, okay, we're going to do some intuiting here. Okay, square root of n and square root of n plus 1 are basically the same, okay, up to a constant. Okay, they're basically have the same behavior. Okay. And so if we think about the highest order terms that appear here, we have stuff that looks like square root of n to the 3 over 2. Excuse me, n to the 3 over 2. And so we can reason here, or you can go ahead and multiply and divide by, let's go ahead and write this out here. If you multiply and divide top and bottom here by n to the 3 over 2, okay, so let's write that in here. If you do this step here, you can show that indeed this limit is 1. Okay, that limit is 1. We know that the reference series is convergent, and therefore we claim this sum is convergent by the limit comparison test. Okay, so this one we have to do a little bit of priming just to get this into a form that is manageable. And now we'll go and finish this off with the last problem. Last one here. This one was a doozy. This one took a while to rehearse here, okay? 1 over n squared minus n cosine of n, okay? Now, I see that n squared there, okay? And I know that, cosine of n wobbles between minus 1 and 1. So that's going to be like a 1. And n squared minus n for large n, well, the n squared is going to win. So I'm going to take a guess here, okay? So we're going to try limit comparison test, and we're going to try 1 over n squared. We're going to compare this against 1 over n squared. Okay? But we're not going to do it in the way that you think, okay? Now, if you remember the statement of the theorem, okay, it just says you have these two sequences, an and bn, okay? You want to do this ratio. It doesn't tell you like how you should label them. Usually what we've done here is we selected bn as our reference series. It actually doesn't matter. What I'm going to instead do is I'm actually going to call 1 over n squared. I'm actually going to go ahead and call this one my an. What? But that's our reference. I understand. But the theorem says it doesn't matter how you label them. So that means we're going to call this thing our bn. Okay, the mystery thing is actually going to be our bn now. Why? The division is just going to work out a lot nicer. Okay, so let's take a look at this. Okay, so we have the limit as n goes to infinity of an 1 over n squared times the reciprocal of bn, n squared minus n cosine of n over 1. Okay, now I'm going to do some operations here. So we'll have the limit as n goes to infinity of n squared minus n cosine of n over n squared. And now, because I have stuff over a common denominator, okay, I can go ahead and split the fraction up and take a look here. We have the limit as n goes to infinity of 1 minus cosine of n over n, okay, a common factor of n drop there.
Now, the first term, that's easy. That's a constant. But what about cosine of n over n? You can show, using the squeeze theorem, okay, if you kind of remember that, or by doing some estimations here, you can show that this limit, or you can also intuit it, you can also intuit that that thing, that second term, that's going to go to 0. So the limit here is 1, but we know that this thing is a convergent p-series. So what did we just show? Because we got a constant that was non-zero, that was finite, that was positive, out of this limit of the ratio here, we have that the sum converges. Okay, this one really takes a bit of thinking, but again, it does not matter how you label your references. Okay, it does not matter how you label your references. So that was quite an excursion. But we saw how to use these things, right? Okay, doesn't matter if you can use the limit comparison test or the direct comparison test. Maybe one of them is going to be much easier to use in the long run. It does give us, however, another way to test for the convergence of certain series. And so now we have added to our toolbox. Okay, as you saw, the limit comparison test is probably the most versatile one because it doesn't require any ordering, but you have to be very careful with those hypotheses, okay? Then direct comparison test can also be powerfully used, but you have to be careful with the way that the inequalities work. Okay? Now, we saw a lot of these, okay? But we still got a lot of tools to fill into our toolbox. And you'll see that not every tool is created equal. Some are more strict than others, as we saw with like the integral test. And for that, I'll see you in the next one.